Good afternoon. Thank you, the chairman, for the introduction. The other author of this work are Andrea Resente and Professor Meneghetti from University of Padova, and Fiorella Trivellin from Electrolux, Italy. Just a quick introduction. It's well known that nowadays short fiber reinforced composite structural application is becoming popular thanks to their strength to weight ratio, their low manufacturing cost, and so on. Recently, the impact of polymers on the environment can be reduced by using recycled polymer, and also the introduction of a fraction of recycled material helps to achieve cost reduction. And therefore, the aim of this experimental work is the investigation of the fatigue behavior of 25% weight short glass fiber reinforced recycled polypropylene filled with mineral filler. In more detail, the material is 53% recycled polypropylene reinforced by 25% weight glass fibers and filled with 21% weight calcium carbonate. Notch specimen, net shape notch specimen were obtained directly by injection molding, while the plain specimen were obtained by machining the final geometry by starting from rectangular plates obtained directly by injection molding. In more detail, tension compression fatigue tests were carried out by using 5mm thick specimens with different notch radius, ranging from 0.2 up to 10 millimeters. That means with a theoretical stress concentration factor that range from 8 to 1.7. The tension fatigue tests were carried out on plain specimen, just on plain specimen at the moment, starting from 1.7 millimeter thick specimen obtained by cutting the specimen by the central part of rectangular plates in order to have a good fiber orientation with respect to the injection direction, and two different orientation specimens having two different fiber orientation were considered, namely 0 degree and 90 degrees. Stress control fatigue tests were carried out by using an axial machine test with a load cell of 5 kilonewton, and two different load ratio were considered: -1, that means tension compression fatigue, and 0.05, that means tension fatigue. The frequency tests were ranged between 4 and 10 Hertz, depending on the applied stress amplitude, in order to maintain the material temperature between 22 and 27 Celsius degrees. The material temperature was continuously monitored by using a thermocouple that was glued in the middle of the next section. Then, in order to monitor the fatigue damage during the fatigue test, we have used two optical microscopes positioned with an angle of 90 degrees one with respect to the other one, in order to detect the damage evolution from a lateral view and a front view. Here you can see just an example of typical damage evolution. We can see here a crack which starts from the crack tip and then propagates across to the next section up to the final failure. In more detail, some example of the damage mechanism that we have observed during the fatigue test. Here you can see the case of tension compression fatigue in the case of 10 millimeters notch radius and a medium fatigue cycle regime. And the picture are taken in this case from the lateral view. Here you can see the no damage situation, that means 0 number of cycle. And the classical damage evolution was characterized by material whitening due to the craze formation, which coalesce to making some cracks, microscopic cracks of the order of some tenths of millimeters, which propagate up to the final failure, giving this final situation. Another example, always in the case of tension compression fatigue, but in the case of high cycle fatigue, And always in the case of 10 millimeters notch radius, in this case, the pictures are taken from the front view. And we can see here again the same damage evolution, material whitening, followed by some cracks, which nucleates at a microscopic scale, which propagates across to the next section, giving the final failure of the specimens. Here again, another example in the case of tension fatigue. At the moment, we have tested just plain specimen, therefore we don't have any example in the case of notch specimens, but we can see here the classical damage evolution that we have observed. Here we have zero number of cycles. That means at the beginning of fatigue test, material whitening, and then some microscopic cracks which propagates, giving the final failure. In the case of plain specimens, both in the case of tension compression fatigue and in the case of tension fatigue, in the case of plain specimens, when we are able to detect some microscopic cracks, practically we have already at the end of the fatigue test, because in the case of plain specimen, there is no propagation phase from an engineering point of view. Now, we move to the microscale in order to analyze deeply the damage mechanisms occurring during fatigue tests. Here in the case of plain specimen under tension compression fatigue and high cycle fatigue regime. We can see here the classical damage mechanism. That means matrix plastic deformations, fiber matrix debonding, some fiber pullouts, and some fiber fail due to fatigue loading. The same damage mechanisms were observed also in the case of notch specimens. Here we can see there's an example in the case of 0.2 millimeters. Here we are exactly at the notch tip. Here we can see the notch and the fracture surfaces. And we can see also in this case, we are in a case of high cycle fatigue regime. We can see again fiber matrix debonding, fiber pullout, some matrix plastic deformation, and here we can see some fiber failed probably due to the fatigue loading. And the same damage mechanisms were observed also in the case of tension fatigue, as you can see here in the case of medium cycle fatigue regime. We can see here fiber failure, fiber pullout, fiber matrix debonding, and matrix plastic deformation. In this case is more evident because in the case of tension fatigue, we have now the pressed effect during the compression phase of fatigue loading, and therefore the matrix surface, it seems rougher than in the case of tension compression fatigue. But now we want to answer to this question. For example, this fiber is a fiber failure to the fatigue loading, or is just a fiber extracted in the final part of the fatigue life during the static fail at the end of the test. In fact, in the case of short fiber reinforced composite, it is well known that we can see different damage mechanisms acting during the fatigue test, and we can find some fibers that are failed due to the fatigue, but also some fiber tips that are extracted from the matrix, therefore they are not failed due to fatigue loading. In order to answer to these questions, we have analyzed both the fracture surfaces, taking at the CEM microscope, taking images at high magnification, and then stitching them in order to have the entire crack initiation zone, but also at high resolution in order to detect in deeply what happens during the crack initiation propagation. Here you can see an example in the case of 0.05 fatigue loading, that means tension fatigue. And we have defined a proper reference system, and both the fracture surface were analyzed. And we have looked at the pairs, for example, fiber to fiber pairs or fiber to matrix hole pairs, in order to understand what happened during the fatigue life. here you can see some example of pairs. For example, pairs number 8 to 8, 7 to 7, 6 to 6, with respect to the axis symmetry. This is the one fractal surface. Here we have the other fractal surface, and then we can evaluate better what are the damage mechanisms. Here an example. We can see here in position number 8 we have fibers, and the corresponding position is here, where we can see a hole in the matrix. Here the same. We can see here in position number 7 a fiber, but in the symmetric position number 7, we can see a hole in the matrix, and so on. Also here, position number 6, we can see a fiber, but in the position number 6, we can find a hole in the matrix. Therefore, here we are in this condition. There are not broken fibers, but just extracted fibers, probably at the end of the fatigue life. In position number 6, for example, we can see here a fiber and also a fiber in the symmetric position number 6 in the other fractal surface. That means that this is a fiber that is failed to the fatigue loading. Therefore, for this example, exactly this specimen, we have counted 396 pairs, but just 38 fibers were broken due to the fatigue loading, which correspond to the 9.6% of the entire fibers that we have analyzed that were broken due to the fatigue loadings. We have done this exercise for different conditions, different notch radius, and both the load ratio that we have tested. And we can conclude that the same damage mechanisms were observed for plane and notch specimens and for the different load ratio, and that the fatigue damage nucleates and procreates mainly in the matrix with a reduced number of broken fiber due to fatigue loading. Therefore, I can move to the conclusions. This work, we experimentally investigated the fatigue behavior of 25% weight short glass fiber reinforced recycled polypropylene filled with a mineral filler. And the fatigue cracks nucleate and propagate mainly in the matrix. The main damage mechanisms were matrix plastic deformation, fiber pull-out with a reduced number of broken fiber, about 10% for this material. And this number, this fraction, it was independent on the notch geometry and the load ratio. Thank you very much for your attention.